we start our discussion on module 1 of chapter 8 now. The main topic of chapter 8 is the fundamental theorem of integral calculus for Lebesgue integration, which we are going to prove, and we will show that the fundamental theorem of integral calculus for Riemann integration can be modified to a much stronger form for Lebesgue integration. But before going into the main results, we need some more results on Lebesgue integration, which are going to be the main topics of this module. So, we start with the first slide of this module. So, we start with our first result. If f is a non-negative function which is Lebesgue integrable over a measurable set E, then for epsilon greater than 0, we can find a delta greater than 0, such that for every set A subset of E with mu A less than delta, we have integral over A f d mu less than epsilon. So, in other words, given epsilon greater than 0, I can choose a delta greater than 0 whenever we take a measurable subset of E whose measure is less than delta. The value of the integral of f over the set A becomes arbitrarily small, that is, it becomes less than epsilon. We start the proof. So, first suppose that the function f is bounded. Now, this means that there is a positive real number capital K such that mod f x is less or equal to capital K for all x belonging to E. Now, let us choose delta in this way: 0 less than delta less than epsilon by capital K. Now, if A is a measurable set in E such that measure of A is less than delta, then we have integral over A f d mu. This is less or equal to integral over A capital K d mu, because the value of f x is always less or equal to capital K, and the right hand side is equal to K into mu A, and this is again less than K into epsilon by K. So, the end product is epsilon. So, we have the result that for that particular choice of delta, whenever I have a measurable set A with measure less than delta, we have the value of the integral over A is also less than epsilon. Now, assume the arbitrary case that f is not necessarily bounded. For any positive integer n, as before, let us define the function f n x as f x when the value of f x is less or equal to n and equal to n otherwise. So, as we have said earlier also, it is like cutting the graph of f by the horizontal line at the height of n. And we know that since f is measurable, so this f n is also measurable, and further the function f n is bounded, since it is bounded by the natural number n. And of course, the sequence f n, n belonging to capital N, this is a monotonically increasing sequence of functions, and it converges to f at each point of E. We have already seen the logic behind this, because if we take a point x where f x is finite, then we can always choose a positive integer m such that f x is less than m, and consequently for all n greater or equal to m, we have f n x equal to f x. So, we have a constant sequence which is convergent to f x, and if takes the value infinity at the point x, in that case for each n, f n x equal to n, which in any case tends to infinity. Now, we can apply monotone convergence theorem on this sequence of monotonically increasing sequence of measurable functions f n, and by monotone convergence theorem we have integral over E f n d mu, this converges to integral over E f d mu. So, from the definition of convergence, choose a positive integer m 1 belonging to capital N such that integral over E f m 1 d mu is greater than integral over E f d mu minus epsilon by 2, because again see that since f n is monotonically increasing, so integral over E f n d mu is a monotonically increasing sequence of real numbers, and its limit is the supremum of all the numbers, that is integral E f d mu is the supremum of integral f n d mu. So, from the definition of supremum we can get this relation, and this means that integral over E f minus f m 1 d mu, this is less than epsilon by 2. Now, let us choose our desired delta in this way: 0 less than delta less than epsilon by 2 m 1. See that when epsilon is fixed, the positive integer m 1 is also fixed. Now, if we take a measurable set A, subset of E, such that measure of A is less than delta, this implies that integral over A f d mu, I can write f as f minus f m 1 plus f m 1. So, integral over A f d mu equal to integral over A f minus f m 1 d mu plus integral over A f m 1 d mu. This is less than integral over E f minus f m 1 d mu, because A is a subset of E, and the second term we have already seen, this is less than m 1 into mu of A, because the function f m 1 is bounded by the positive integer m 1, and the end product is less than epsilon by 2 plus epsilon by 2, and this is equal to epsilon. So, this shows that we have again for any arbitrary measurable function f, also given epsilon greater than 0, I can choose a delta such that whenever measure of A is less than delta, the value of the integral is less than epsilon. And from the above result, we can get this particular corollary. If f is Lebesgue integrable over a measurable set E, then for epsilon greater than 0, there is a delta greater than 0, such that for every set A, of course measurable, subset of E with mu A less than delta, we have integral over A mod f d mu is less than epsilon. The proof follows from the fact that any real function f can be written as f equal to f plus minus f minus, where as before f plus is the positive part of f and f minus is the negative part of f. And we have already seen that f is measurable if and only if f plus and f minus both are measurable, and mod f is equal to f plus plus f minus. And both f plus and f minus are non-negative measurable functions defined on E. So, we can apply the last result on both the functions f plus and f minus. In other words, for a given epsilon greater than 0, we can choose for the function f plus say delta 1 greater than 0, and for the function f minus say delta 2 greater than 0, such that integral over A f plus d mu is less than epsilon by 2 whenever A is a measurable subset of E with measure less than delta 1, and integral over A f minus d mu, this is less than epsilon by 2 whenever we take a measurable subset A of E with measure less than delta 2. Now, as in many cases in analysis, let us choose delta as the minimum value of delta 1 and delta 2, and then it is easy to observe that whenever we take a measurable subset A of E whose measure is less than delta, we get integral over A mod f d mu. This is equal to integral over A f plus d mu plus integral over A f minus d mu, because we know that Lebesgue integration has this property that integral f plus g equal to integral f plus integral g, and the right hand side each of the term is less than epsilon by 2. So, the sum is less than epsilon, and this proves our assertion. We now present a result which states that if f is a non-negative Lebesgue integrable function on closed interval a b, then integral a to b f d mu is equal to 0 if and only if the function f is equal to 0 almost everywhere in closed interval a b. The proof is not given here, the proof is quite easy. The logic is like this, that suppose that integral a to b f d mu is equal to 0. On the contrary, suppose that f is not equal to 0 almost everywhere. But this means that the collection of all points x where f x is strictly greater than 0, this set has positive Lebesgue measure. But the collection of all points x where f x is greater than 0, this set can be expressed as countable union of sets of the form collection of all x where f x is greater than 1 by n. So, from the countable subadditivity of Lebesgue measure, it follows that there is at least one positive integer m for which the set x belonging to closed interval a b where f x is greater than 1 over m, this set has positive Lebesgue measure, say alpha, and consequently it is easy to observe that integral a to b f d mu is greater than alpha by m, and this is a contradiction. And similarly, we can show that if f is equal to 0 almost everywhere in closed interval a b, then integral f d mu over a b is equal to 0. So, we have seen that for a non-negative Lebesgue integrable function, the integral is equal to 0 if and only if f t is equal to 0 almost everywhere. But what happens if the function is not necessarily non-negative, that is, if we take an arbitrary Lebesgue integrable function and the result is this, that if f is Lebesgue integrable on closed interval a b, then integral a to x f t dt is equal to 0 for all x belonging to closed interval a b, if and only if f t equal to 0 almost everywhere on closed interval a b. So, you can see the difference between the last result and this result. So, for a non-negative function, we need to have only one integral equal to 0 to have f equal to 0 almost everywhere, but for an arbitrary Lebesgue integrable function, for f to be 0 almost everywhere, we need that every integral a to x f t dt should be equal to 0 for all x belonging to closed interval a b. So, we start the proof in this way. Of course, if f is equal to 0 almost everywhere in closed interval a b, then obviously f is equal to 0 almost everywhere in closed interval a x for any x belonging to closed interval a b, and consequently integral a to x f t dt is equal to 0 for all x belonging to closed interval a b. Conversely, suppose that the condition holds, that is integral a to x f t dt is equal to 0 for all x belonging to closed interval a b. We need to show that the collection of all those points x belonging to closed interval a b where f x is not equal to 0, this set has Lebesgue measure 0. Suppose on the contrary that f x is greater than 0 on a subset E of closed interval a b which has positive Lebesgue measure, because the collection of all those points where f x is not equal to 0 can be divided into two parts, where f x is greater than 0 and f x is less than 0, and we are taking the first part. Now, from the property of measurable sets, recall the definition of inner measure. So, we can find a closed set F contained in E such that mu f is also greater than 0, because we know that the measure of E is the supremum of the measures of all closed sets contained in E. Let O equal to open interval a b minus f. See, f is a closed set. So, if we take the difference between an open set and a closed set, we have an open set. Now, by our assumption, integral a to b f d mu is also equal to 0, but the whole interval is divided into two parts, O and F, and in any case the 2 point set A and B, it has measure 0. So, we have integral a to b f d mu equal to integral over f d mu plus integral over O d mu, and consequently integral over O is equal to minus integral over f, and this is not equal to 0. Now, since O is an open set of real numbers, so we know that O is the union of a countable collection of mutually disjoint open intervals a n b n, n belonging to capital N, and consequently integral over O f d mu, we can write it as sigma n integral over a n to b n f d mu, but the whole sum is not equal to 0. But this shows that at least for some positive integer m, integral a m to b m f d mu should not be equal to 0, because if every integral a n to b n f d mu is equal to 0, then the whole sum is also equal to 0, which is not the case. But this means that integral a to b m f d mu minus integral a to a m f d mu, this is not equal to 0. So, the difference of two real numbers is not equal to 0. This again implies that at least one of the two real numbers should be not equal to 0. So, this implies that at least one of the integral a to b m f and integral a to a m f must be non-zero, which is a contradiction to our assumption, because our assumption was that for any x belonging to closed interval a b, integral a to x f is equal to 0. So, this proves our assertion. Similarly, if we assume that f is less than 0 on a set of positive Lebesgue measure, we can arrive at a contradiction, and so we have that f equal to 0 almost everywhere in closed interval a b. So, to summarize, what we did in this module is that we have established certain properties of Lebesgue integral. The main two results which we will also need in the later modules is that first, if f is Lebesgue integrable on closed interval a b, then for any given epsilon greater than 0, there exists a delta greater than 0, such that whenever we take a measurable subset A whose measure is less than delta, integral of f over A is less than epsilon, we will see that this property actually implies the continuity and more importantly uniform continuity of a particular function. And the second result which we have established is that for a function f, the function f is equal to 0 almost everywhere on closed interval a b. If integral a to b f d mu equal to 0 when the function is non-negative, and integral a to x f d mu equal to 0 for all x belonging to closed interval a b when the function is not necessarily non-negative, that is for an arbitrary integrable function. And with this we end this module.